Hello, I am Fernando Martín from Universidad Autónoma de Madrid, and I'm going to chair the second session of this workshop that is devoted to high harmonic generation in gases and solids. So it's my pleasure to introduce the first speaker of the session, who is Carlos Hernández Garcia, who is going to speak about shaping high-order harmonic combs through phase-nickel drivers. And before he starts, let me emphasize that you are welcome to type your questions in this Q&A button that you have. Please, if you have questions, please start typing them before the end of the session, because the usual problem is that at the end of the session you don't have time to type everything, and then only the chair asks questions. So if you have any questions at any time, please start typing the question as soon as possible. So Carlos, please. The stage is yours.
Thank you very much, Fernando. Hello, everyone. Let me first thank Francesca and Fernando and the scientific committee for giving us the opportunity to present our work here today. And I will present our recent work that we've performed at the University of Salamanca in collaboration with our colleagues at the University of Colorado at Boulder, about shaping higher harmonic cones through phased necklace drivers. And we did it using harmonic generation in gases. So before entering into the more specific topic, I'd like to comment a bit on harmonic generation in gases, as lately, at least me, I've been asked several times the question, are we done with harmonic generation in gases? Well, it's certainly amazing that all the advances that we've done over more than 30 years in the understanding of the mechanism and how we have exploited it towards the generation of arosecond high harmonic sources. But for me, there's something remarkable of harmonic generation. It's coherence, spatially and more importantly, temporally. Thanks to the unique coherence of the harmonic generation process, after more than 30 years, we can still advance substantially in not only in uncovering new physics, as we heard beautiful talks this morning by Anne and Pascal, but also in tailoring the properties of the harmonics and arosecond pulses. And in that sense, one of the most attractive trends nowadays is to generate structured harmonics. And by structuring harmonic sources, I mean to spatially tailor its intensity, phase, and polarization properties. These structured harmonic pulses are very interesting for laser matter interaction at the nanoscale, with prospects in different fields, such as in ultrafast magnetism, in the study of ultrafast dynamics of inertial processes, in the study of chiral nanostructures, or in nanometrology, among others. So structuring can be understood in terms of the spin angular momentum in case of polarization and in orbital angular momentum in the case of the spatial intensity and phase distribution. So as a brief reminder, I remind you that light angular momentum exhibits two different properties. Spin angular momentum related to polarization. You all know we can have a spin 1 or -1, left-handed or right-handed polarization, circular polarization, and then orbital angular momentum, which reflects the spatial variation of the phase of the beam. And it is characterized in terms of this quantity here, which is the topological charge, and it relates to the number of phase jumps, 2p phase jumps that we have along the transverse profile of beams carrying orbital angular momentum. Of course, they have a singularity at the center. That's why the intensity profile, we have these well-known dotted profiles. Okay. So during the last decade, we have achieved an extraordinary control over the spin and orbital angular momentum of harmonic beams. In particular, with the spin angular momentum, we know already how to produce elliptically polarized harmonics by using anisotropic media or by using two-color linearly polarized drivers. We also know how to produce circularly polarized harmonics and arosecond pulses by using this well-known bicircular field in a collinear configuration, also by using a non-collinear approach in which we were able to generate isolated circularly polarized arosecond pulses, or even by combining two harmonic sources. in most of those schemes, the coherence property of the process is fundamental. Yeah, we are able to generate harmonics with polarization different from linear polarization by properly modifying the driving beam of the harmonic generation process. On the other hand, we have also achieved grid control over the orbital angular momentum in the process of harmonic generation. We know how to produce harmonics with orbital angular momentum in gas targets in a wide variety of configurations, with single orbital angular momentum or with multiple orbital angular momentum contributions. We also know how to generate harmonics with both spin and orbital angular momentum, and even how to produce harmonics with time-dependent orbital angular momentum. Okay, so if you want to have a more in-depth characterization of this spin and orbital angular momentum, I just remind you to this talk we had in this cost network in the last winter school. Okay, and today I will change this a little bit, and again, in all those schemes, we were able to achieve control over the angular momentum of the harmonics through the angular momentum of the drivers. Today, I will show you that we can also gain control over other properties, such as the frequency line spacing and the divergence of the harmonics, purely through the angular momentum of the drivers. Okay, so let's start about what is this control over the frequency line spacing of the harmonic combs. How can we control the line spacing of the harmonic combs? Well, in the most general case, you know that harmonic combs are composed of odd order harmonics, so the line spacing between the harmonics and the combs is 2 times the driving frequency. However, for many spectroscopy applications, it could be desirable to control such harmonic spacing. For example, it might be very interesting to increase the spacing between the harmonics to 6, 10 omega, 14 omega, or let's say, for example, 18 omega. But such control is not trivial at all, okay? And to understand the complexity of such control, let me review the basics of harmonic generation. Yeah, harmonic generation spectrum is typically composed of odd-order harmonics, as I said, which is a direct consequence of having 2 emissions per cycle. And the origin of this lies in the symmetry of the electric field and the target. Here we are considering an atom, so the 2 rescarriages that we have per cycle leads to the generation of pulse trains with half a period separation between them, and thus to an harmonic frequency comb with a line spacing of 2 omega. Okay, I think that's clear, yeah? So if we would like to generate a spectrum of, for example, frequency spacing of 10 omega, it means that we would need to have 10 events per optical cycle, which seems quite impossible in the harmonic generation picture. How can we do this? How can we obtain more than 2 events per cycle? So the answer I told you today lies in the macroscopic response. Okay, so we all know that at the microscopic level, we can understand harmonic generation from the nonlinear interaction between the driving field and the atom. Yeah, but however, in an experiment, we have a gas jet. We have many, many atoms. And of course, the driving field and thus the harmonic emission can differ substantially from atom to atom. And thus, phase matching between the different harmonic sources needs to be taken into account. We can distinguish between 2 kinds of phase matching. Yeah, typically between longitudinal phase matching, yeah, in which we have a longitudinal array of harmonic emitters whose phase varies along the longitudinal direction. But we can also have what we call transverse phase matching, yeah, where the phase varies along the transverse dimension to propagation. Of course, this is a very simplified picture, and to gain better understanding, here I've mentioned some references, but you can find many more about it. Typically, in these schemes, we are concerned about efficiency. We are concerned about constructive interference between all these harmonic sources. But let's try to change this a little bit. Can we modify the properties of the resulting harmonics by properly combining the radiation from different atoms? There have been already different works, yeah. For example, these two here, in which by using, in this case, two gas jets or two focal spots in the same gas jet, in these works, one can tailor the polarization properties of the harmonics that are emitted. But here I will show you an alternative to gain control over the harmonic properties. Instead of, for example, instead of placing two different gas jets, two different targets, we can properly tailor the phase of several harmonic sources thanks to the orbital angular momentum of light. Actually, we propose to generate what we call a transverse array of harmonic emitters through the use of a phased necklace beam. For example, in this case, I show you a phased necklace of 5 lobes or bits, each of them with a different phase content. Remember that we were interested in controlling the line spacing between the harmonics. So the idea here is quite simple. Now, each of the lobes will produce harmonics, but with a different phase or time delay according to the phase of the corresponding lobe. So if now we consider the far-field radiation that is detected on axis, such radiation is the result of the coherent addition of the harmonics coming from each lobe, each of them with its phase. Due to their different phase or different time delay, we can obtain such an emission pattern, as you see here, with a separation between each event, in this case of a tenth of a period. Of course, this now corresponds to a frequency separation of 10 omega. Another point of view to understand this effect is that you can think that only certain harmonics in our cone of high-order harmonics will present constructive interference on axis when they are detected on axis. So now the question is, how can we produce this phased necklace? How can we produce it? We can do it very simply. We can do it with a combination of two drivers with opposite and non-degenerate different orbital angular momentum. So for example, in this case, to have this phase necklace of 5 different lobes, we are combining two drivers with L equal 2 and L equal -3. And to predict the correspondence between the orbital angular momentum of the drivers and the harmonic line spacing, sorry about this, we can easily invoke orbital angular momentum selection rules to try to predict the line spacing of the harmonics in terms of the orbital angular momentum content of the drivers. So, for example, let's invoke orbital angular momentum selection rules, and let's consider our driving field composed of two different beams with opposite and non-degenerate, which is different, topological charges. If we calculate now the topological charge of the qth order harmonic as a function of that of the drivers, and then we impose the condition that the harmonics are detected on axis, which means that the topological charge of that harmonic is 0. After some basic maths, we can obtain the harmonic frequencies that are detected constructively on axis, which are those here, and to calculate the line spacing of the harmonics as a function of what? As a function of these quantities which depend on the orbital angular momentum of the drivers. This was what we were trying to obtain. We were trying to obtain the frequency line spacing as a function of the orbital angular momentum of the drivers. Note that this quantity here is defined as the least common multiple of L1 and L2. Okay, so for example, if we have this example of L1 equal to 1 and L2 equal to -1, the predicted harmonic line spacing will be of 6 omega 0. And to predict and to corroborate it, we perform theoretical simulations, theoretical simulations of harmonic propagation, harmonic generation that, of course, need to include the macroscopic response, need to include propagations. And for these results, just to let you know that they were done in argon at 800 nanometers. Those are the intensity spatial profiles of the different harmonics, but it is also relevant for us to look at the orbital angular momentum content of each one of the harmonics, which can be easily done by performing the Fourier transform along the azimuthal coordinate. Yeah? And you can see in this case that only harmonics 15th and 21st present harmonic emission on axis at the center. And if we look at the orbital angular momentum content, you can see that L equals 0. Yeah, also here, L equals 0. It's only achieved on axis for harmonic 15 and harmonic 21st. The other harmonics, they are generated, but their emission is off axis, which means that they have other contributions of orbital angular momentum. So thus, if we now select spatially the emission that is detected on axis, and we can do this very easily with just a spatial filter, we can obtain an harmonic cone with the line spacing that was predicted by theory. Let's see this in a little bit more in detail. So what we can do, we can plot the line, this rule that we've obtained, this line spacing as a function of the orbital angular momentum of the drivers, which clearly shows the control we have over the line spacing as a function of just the orbital angular momentum of the drivers. So here I show you results for helium, as a target, 800 nanometers. Those are results from our simulations, from our theoretical methods. And here I show you the results for different orbital angular momentum combinations. And by following this prediction here, you can see that in fact this prediction is obtained. The harmonics that are detected on axis, we can tune the line spacing purely by tuning the orbital angular momentum content of the two drivers. Such control is particularly interesting if we use longer wavelength drivers. Why? Because it's known that we go with mid-infrared wavelength drivers, we can increase the photon energy towards the soft X-rays. And in this particular region, optics are very limited. So for example, if we use a 2-micron driving wavelength, we can obtain controllable harmonic cones. We can control the line spacing of the harmonic cones up to energies up into the close to 1 kilo electron volt, as you can see here, well, in this case 600 electron volts farther than the water window. Okay, so our colleagues at the Captain Murnane group at GLA, University of Colorado, they performed the experiment to corroborate this novel control. And here you can see the nice agreement between the theory and the experiment of the experiments performed in argon, again with these drivers I showed you before, L1 equal 1, L2 equal -2, with this line spacing of 6 omega 0. And you can directly see that if we focus on the harmonics that are emitted strictly on axis, you can see that the line spacing obtained in the experiment is exactly that predicted by theory. So again, I would like to focus that yes, we can control the line spacing of the harmonics just by controlling the orbital angular momentum content of the driving fields. Okay, so finally, another very interesting aspect of this novel control, and I would like to bring your attention here, is a nice feature of these necklace-driven harmonics. In contrast to standard Gaussian-driven harmonics, the divergence of necklace-driven harmonics decreases with the harmonic order. In standard Gaussian-driven harmonics, if we look at the divergence, it increases with harmonic order. However, here it decreases, which is, as you can imagine, particularly interesting. Why is this happening? Okay, in Gaussian-driven harmonics, in the near field intensity region in which harmonic are generated, this near field intensity region, of course, decreases with the harmonic order, as the intensity required to achieve higher harmonic orders, it's higher, okay? That's the reason why if the near field intensity region decreases, then the far field detected divergence increases. Even it's interesting that this effect even dominates over the wavelength behavior. Of course, we are reducing the wavelength, however, this effect here dominates. So it's really difficult to achieve low divergence, high order harmonics with the Gaussian-driven harmonics. However, in necklace-driven harmonics, the intensity ring where all the harmonics are generated is constant for all the harmonics, and thus the far field divergence decreases with the harmonic order as the wavelength is shorter. Yeah. Actually, this divergence follows this very simple law here, yeah, where this quantity here is the important one, R, is the radius of this ring. Of course, this radius is exactly the same for all of the harmonics, so we can really, the divergence really decreases with the harmonic order, okay? So here I show you theoretical simulations, okay, of the divergence versus the harmonic order for different shaped necklace configurations, different combination of orbital angular momentum, and also in gray for a Gaussian driver focused at different positions. So first, you can see in general that the behavior in which the divergence decreases with the harmonic order is perfectly followed for all the cases of necklace-shaped harmonic generation. It's also corroborated by this very simple analytical estimation in orange. And on the other hand, for Gaussian-driven harmonics, even if we play with the position of the focus and the gadget, and there are very interesting works in which we can tune the divergence by playing with the gadget position and the focus, even if we play with it, you can see that the trend is that the divergence increases with the harmonic order. You can readily imagine that this is particularly interesting if we go towards higher harmonic orders, even if we go, as I showed you before, into the X-rays, where the focusing optics are very limited. Yeah, actually, we look closely to a couple of harmonic orders. Here, the 27th here and the 45th here. You can see the difference in the divergence of the necklace-shaped harmonics for different combinations, as you can see here, and the Gaussian-driven harmonics. Yeah. Okay, and also our colleagues at the University of Colorado at Boulder, they performed the experiment. They also looked at the divergence, and again, this is what they obtained. This is the two cases for the 15th harmonic and for the 21st harmonic. And if we compare the Gaussian-driven harmonics in gray and the necklace-driven, for the case I showed you before, L1 equal 1, L2 equal -2, you can see that the divergence is really shorter for the necklace-driven harmonics. Yeah. Okay. Good. So I think that with this, I hope I've convinced you that in this case of Gaussian necklace-driven harmonics, we can both tune the line spacing and we can control the divergence. And one important thing that is here, you can already have asked this yourself, is, okay, what about the efficiency? What about the brightness of this necklace-driven harmonics? So you can see here the comparison. The comparison is quite fair. Yeah, the brightness of necklace-driven harmonics is comparable to that of a standard Gaussian-driven harmonics. Yeah, and this was also shown in theory, but it has also been corroborated by our experimental colleagues. Okay, so just to finish, I would like to mention a couple of two very interesting different work we are developing here at the University of Salamanca. We are also trying to understand a new kind of structured extreme ultraviolet beams, which are combining the properties of vector beams, but also the properties of vector beams, which are polarization-shaped beams. And we are doing this in collaboration with our colleagues at Paris-Sinclair, who have developed the inclusion technique in order to try to understand the dynamics of those beams. The propagation dynamics are not are quite complex, but they are really, really interesting how we can merge these properties of both vector and vortex beams. And finally, also at the University of Salamanca, we are trying also to study from a theoretical point of view and try to bring what we learned from structured light in gases to solids. Yeah? We are now exploring how targets, for example, a graphene layer, can be engineered to imprint orbital and spin angular momentum. Yeah? Solids are much more complex systems. There are many things that they need to be understood there, but it's really nice that bringing all this field of structured light, we can understand them in a much clearer way. Okay, so finally, I would like, of course, to mention the people involved in this work. I would like to present my group at Salamanca, the Laser Applications and Photonics group, and in particular to present the people that is involved in the theory of harmonic generation and arrowsecond science. For the work I've presented today, a lot of credit goes to Laura Rego, who just defended her PhD in the work of, and he was very involved in the work of nucleus-driven harmonics. Also, this couple of latest works I presented about vector vector space have been done by Alba, and also what we are doing in graphene with Anna and Oscar, and also Roberto is involved. And of course, also I would like to thank Luis Plaja, Julio and Roman, which have been involved in this work. I would like also to thank our collaborators, in particular the group of Captain Morning at the University of Colorado at Boulder, and Nathan and Quinn, who were in charge of the experiments I've presented today. And okay, I would like just to conclude. I hope I've convinced you that nucleus-shaped harmonic in gases is a very elegant way to control in a novel way the line spacing properties and the divergence of the high harmonic cones. So thank you very much for your attention. And now I'm open to any questions you may have.
Okay. Okay. What? No? Okay. Okay, thank you. Sorry, I don't know. There is some echo that I don't understand. Anyway, thank you very much, Carlos, for the presentation. We have a question already by Carlo Calegari. The question is for the harmonic cones with separation n larger than 2. How does the energy per pulse scale with n? In other words, do we expect them to be considerably weaker than conventional HHG?
Well, what is happening is, I've showed you slightly in one of the last slides, is that if you look at harmonic, the brightness of each harmonic order is comparable. Okay, so you can think that you have the harmonic cone, okay, and you are eliminating some of the harmonics out of our harmonic cone, but the brightness of each one of the harmonics that were already present in the 2n in the standard harmonic cone, it's similar to that obtained in the when we are going to this higher line spacing cones. Yeah. So I hope that this is something that we've seen theoretically, and also in the experiment they've seen this. I hope this may answer your question.
Okay, I don't see other questions. I have one. So, Carl, yes, there is one. Sorry. One by Pascal. Thank you, Carlos, for the nice results. Could you tell us what kind of medium you use in the simulations, experiments, jet cell fiber, and what was the length?
Yes, yeah. In experiment, it's an argon gas jet, a standard argon gas jet. It's, I would say, 1 millimeter with argon gas jet. And in simulations, we've done also argon and helium to go towards the X-rays. Yeah, but I think I would say it's rather a standard gas jet for harmonic generation in gases.
Okay. I'm confused with this. I don't know you can hear me now because I don't hear you. Can you hear me? Yes.
I can hear you,
okay.
Fernando.
Anyway, there is another question by Thierry Rouchon. Very nice talk. When you see all the dots, what are the global and local phase profiles? Can you define an orbital angular momentum on average or locally for each dot?
Well, that's a good question, Thierry. The orbital angular momentum, it's just the composition in this case of, let's say, L equal 2 and L equal -3. Yeah, and if you combine these two beams, you have these 5 lobes, and actually the phase locally in each one of the lobes, it's true, it varies slightly, but it's in the, let's say, at the center of each spot, it's quite flat, the phase there. Of course, there is some phase profile, but we've seen that of course, I'm trying to explain this in simple physics, yeah, with a different addition, but it really works, yeah. I don't think you have enough phase variation in each one of the dots, so you can define locally OAM in each one of them. No, I wouldn't say that. Yeah, the phase variation in each one of the lobes is quite smooth. So I don't think there is a point here to define an orbital angular momentum in each one of the dots. Yeah. We can discuss this later on if you want. It's quite interesting. Yeah.
Okay. So I think we have to stop the discussion here. Thank you very much, Carlos, for the nice presentation and for answering all the questions. And now we move to the second speaker.
Thanks, Fernando.
Who is Katalin Kovacs, and she's going to speak about space-time coupling in high harmonic generation, 2 case studies. So, Katalin, the stage is yours.
Thank you very much. Now I share the presentation and start. Can you see the slides? I hope so. Thank you for the introduction and for invitation. Indeed, I will speak about temporal coupling, which occurs very naturally in macroscopic conditions when we consider also macroscopic conditions in high harmonic generation. And for this purpose, I will very quickly give a reminder about the basics of high harmonic generation and also motivate why macroscopic modeling of high harmonic generation is important. I will tell the basic steps, and I will insist also on 2 additional calculation tools, the time-dependent phase matching calculations and the quantum trajectory analysis, because this will be of great help when I move forward and show 2 nice examples of how we can exploit to fits this inherent space-time coupling in laser atom interaction. Well, when we generate high harmonics, we know that an intense laser pulse is focused in a gas jet or static cell, and here it happens the elementary laser atom interaction, which usually is modeled at very high accuracy level. Then these high harmonics propagate together with the driving field. The driving field has to be filtered out, and many other filters and tools are used. And finally, experimentalists measure hopefully a nice high harmonic spectrum, which is a macroscopic which is created in a macroscopic medium. So why, in the first place, of course, we know the 3-step model, which clearly describes the steps of how high-order harmonics are being generated under the influence of a strong laser pulse. The Coulomb potential is distorted around the atom. One electron can tunnel ionize, it accelerates, accumulates both phase and kinetic energy, and if it has a good chance, it can recombine, and the excess energy is emitted as a high energy photon due to the symmetry, to the half cycle symmetry of the process. As we all know, we have in a temporal structure attosecond pulse train separated by half of the optical cycle of the driving field, and a typical high harmonic spectrum, which usually consists of odd order harmonics of the driving field. But what happens during propagation, why it is needed to introduce in every modeling the macroscopic effects, because this is a clear example how the peak intensity, for example, of the driving pulse and a nice Gaussian shape in space in radial coordinate, it suffers an intensity clamping, and also the Gaussian shape is not valid anymore. And these, for example, in time, this is for the same pulse. We see the black pulse in time was the initial one, the unmodified, and after propagation, it is distorted. It suffers both self-phase modulation and intensity decrease. And all these modulations are also inherited, are transmitted to the dipoles, to the generated dipoles. So while the initial dipole spectrum look like this with a high cutoff, for example, we have at the end of the medium a much reduced cutoff and a different dipole spectrum. So it is important to introduce in the modeling also these macroscopic parameters, and therefore our model, which we use, has the main purpose to faithfully reproduce experiments as faithfully as possible. Therefore, we use as input parameters measurable quantities as far as one can afford to have measurable quantities, what concerns the driving, concerns the geometry of the system, and what concerns the properties of the interaction region. And of course, we would like to make a trade-off between computational efficiency and accuracy, but we always tend to maintain high accuracy as possible. And its structure is like this. First of all, we construct the case according to the experimental parameters, and then follow the logical physical steps which drive such a process, solve the propagation of the pulse in the interaction medium, solve the single dipole response. Here we use the strong field approximation. And then after that, the propagation and the build-up of the macroscopic high harmonic signal is calculated. These are the papers which we rely on, and of course adapt the model for developing experimental conditions. First of all, in order to construct the initial pulse, we have to take into account the spatial envelope, the temporal envelope. We also take into account different phase contributions, not only the GUI phase, but also the radial phase of the pulse. This is for a Gaussian pulse, but we can also use, for example, truncated Gaussian or Bessel type beams, which are very important nowadays, because this is how it comes from a hollow core fiber amplifier. First step in the modeling is that we solve the propagation equation for the driving pulse. Here there are several peculiar interesting things. One is that the unknown field itself is the source term, which means that there is an explicit dependence on the laser path, and therefore we use a self-consistent iterative method to solve this equation. And there is another very important aspect. This is the very much changing effective refractive index of the medium where the laser path is propagating. We account for the linear dispersion and absorption here, and also for the Kerr nonlinearity, and which is most important at very high intensities is this plasma term, which through the free electron density is containing implicit dependence on the driving field. Numerically, it is solved in frequency domain. I don't enter into much detail, just I wanted to stress that through this method, inherently we account for the temporal and spatial distortions, deformations of the driving laser path during propagation, and all these distortions will be transmitted to the single dipole response, which we calculate by the strong field approximation. What is a remark here that we take into account also we take into account the depletion of the ground state through the ionization rate. Again, here it was another workshop where I insisted on the calculation of the ionization rate, which is again a non-trivial problem, but today I won't insist upon this serious problem. So we take into account the ground state depletion. And after this step, well, we have to build the harmonics which are generated in this interaction medium. A very similar equation is solved for the harmonics as for the driving field. It is an important difference that the source term now is the nonlinear polarization calculated in the preceding step, so it is a known quantity already. There is no need for a self-consistent iterative method. And I want to stress that reabsorption in the medium is taken into account for every spectral component, so to say, to every harmonic order. And in order to go from the near field, which is the really end of the interaction medium, to go to the far field where usually the detector is placed, we use the ABCD ray matrix formalism for linear spectral linear optical elements, and use the Henkel transform to transport the near field harmonics to the far field, and to be able to study their spectral, spatial, and temporal properties. Additional calculations which come as support, as help for previous calculations are the phase matching analysis. We know from the seminal paper of Baku that in a static case, complete phase matching, perfect phase matching is obtained when the wave vector of the qth order harmonic is equal to the wave vector of the polarization. And we extended this model in the sense that we take into account the phase of the already modified, the already propagated laser path. And so we do also for the atomic phase. And the time dependency comes that we are able to calculate phase matching conditions for several optical cycles where we are interested to see phase matching conditions and coherence length for several before we obtain such information that is not available experimentally. So these phase terms are all calculated from the propagated solution of the wave equation, and therefore it contains, it's a more general description. Another supporting calculation is the quantum trajectory calculation, where we use and exploit the stationary phase approximation. This is the phase accumulated by the excursion of through the excursion of the electrons, where P is the stationary momentum, and we have to solve a set of saddle point equations, which are complex valued equations. We use approximations, and we can nicely reproduce the trajectories of the electrons. Here I show a simple example where we have elliptically polarized laser field, therefore we can visualize the trajectories. And what I wanted to stress at this method, which is able to treat electric fields of any shape, for example, distorted during propagation, there are classically these red trajectories would be the classical trajectories which are not able to close, while for the same harmonic, the equivalent of the same not closing trajectory, these are the closing trajectory is a short one and a longer one for the same harmonic order. And what is important at these calculations is that we will have direct access to the phase of the electron trajectories, and these will be important at those two case studies which I'm going to show now. So spatial temporal coupling in high harmonic generation is somehow inherent due to the fact that these laser pulses propagate in a nonlinear medium. Therefore, it is very true that we never can decouple the temporal variation from the spatial variation of the driving field. So just as one example, I want to show how the temporal shape of a driving laser pulse modifies differently at different positions in the interaction region, at different radial and different on-axis, different longitudinal positions. So space-time coupling is there. It was considered that is detrimental to the process, to the high harmonic generation process, but let's see whether we can use it. And colleagues know for a long time that, for example, the attosecond lighthouse is one example where we can use this space-time coupling in order to obtain single attosecond pulses without spectral filtering, only by spatial filtering of the successive attosecond pulses. And what I want to show, what I named lighthouse case, that usually attosecond lighthouse is obtained experimentally by introducing a wedge, a slab in the optical path of the laser beam. And now we showed that due to the cell phase modulation, due to the propagation effects, the deformation of the driving pulse during propagation, there are experimentally feasible configurations where, without the insertion of any dispersive slab into the optical path, we can obtain this attosecond lighthouse effect, which means that temporally successive attosecond pulse emissions are emitted at with different divergence, and in the far field they are detected at different positions of axis, and using only spatial filter without using spectral filtering, single attosecond pulses can be obtained, can be filtered. What happens in this configuration, we used a mid-infrared driver because it is known that mid-infrared pulses are more sensitive to the effective refractive index changes. And as we see, the temporal shape modification and both the spatial, here we represented the laser pulses peak amplitude along propagation. We see that after a really short distance of propagation, a so-called self-guided regime is attained by the driving laser pulse, which we hope, and we will show that it is beneficial for the phase matching of the generated harmonics, as we present here the macroscopic, the final near-field spectral our spectrum, that we have harmonics at fairly high energies, high orders, around 100, 130 electron volts. This yield enhancement is particularly important for further experiments. And let's see which is the mechanism of this, or how can we assure that we have a lighthouse type emission. Here we see the temporal radial profile of the driving field, and we see that we have a nice pulse front rotation observed. The rotation is increasing both in time and as we go further from the laser axis. So we have both a temporal and a radial variation of the pulse front rotation. This is due to the fact that the central part of the beam experiences the strongest plasma dispersion and propagates with higher phase velocity compared to the peripheral regions where there is not so high intensity, consequently not so high level of ionization, consequently not so big cell phase modulation, and these temporal and spatial coupled phenomena lead to this wavefront rotation, which is essential ingredient for requirement for the attosecond lighthouse. These wavefront rotation of the driver is transmitted to the generated harmonics, to the harmonic emissions, and this is what I show here in the near field, the temporal radial structure of the emitted harmonics. These are already macroscopically built up harmonics at the end of the medium. You may say, and you're right, that there is no a single attosecond pulse emission, which is correct. This exactly, I showed this configuration because it was not optimized for single attosecond pulse generation. It was only a case study to show that it is possible without the insertion of any slab into the optical path to observe, to obtain this attosecond lighthouse type behavior. But also we have a good contrast ratio. The best contrast ratio was 20:1, and in average we had 10:1 contrast ratio, which is not that bad. The situation is nicer in the far field because these emissions with different divergence in the far field, they arrive at different radial, they are detected at different radial coordinates, and what you see here at the sections, the different colored lines, the emissions here, the integrated emissions are depicted here, and we can say that the attosecond lighthouse type emission has been demonstrated, and successive harmonic emissions are emitted at different distances from the optical axis. Therefore, placing an iris in the far field, almost single attosecond pulses can be filtered out without using spectral filter, because we know very well that this is the weakest point of high harmonic generation, that usually the high harmonic flux is reduced, so we have to take care of every photon which is emitted. The second example which I wanted to show again exploits mid-infrared pulse, because nowadays mid-infrared sources become more and more powerful and more used in the community. This is a similar configuration. We place interaction region in the converging beam such that it ends exactly in the geometrical focus of the configuration of the laser beam. This is a fairly long medium 9 millimeter filled with helium. We chose helium in order to go as high as possible with the cutoff. We target the water window, and what we observed is that interestingly, yes, we use also a very short pulse. This is already feasible experimentally to have in the mid-infrared region such a short few cycle pulse. This was used in order to have also already at dipole level to have only several attosecond emissions. And what was important for us to observe that the macroscopic power spectrum, the near field power spectrum, showed a spectral gap exactly in the region where the water window regime starts. Or in other words to say, we observed somehow a double plateau region, a revival at very high order harmonics, and we wanted to see what happened and which is the structure, both temporal, spatial, and what is the frequency content of these elementary emissions. And we observed a very interesting thing. I apologize for this crowded slide, but it is very important that we interpret all the graphs here in pairs together, because these are the complementary aspects of the same phenomena. The temporal radial map of the generated harmonics says that we have two emissions. A first one concentrated mostly on axis, a second one concentrated mostly off axis. These are cases for different CEP values. Bearing in mind that this is a very short pulse, it is obvious that CEP variation might be important, but in order to catch the idea and for me to understand the phenomena, I will only concentrate on the CEP equals 0 case in order to show this spectral separation, both temporal and spectral separation of the two attosecond pulses. The other way round, the spectral radial map of the same harmonic radiation gives us a hint that emission number 1, which is concentrated on axis, this one, contains only the very high order harmonics. The other way round, emission number 2, which is the later one, which is concentrated mostly off axis, contains only the lower energy harmonics, and there is a spectral gap in between these two emissions. This is an exclamation for us that, well, then we have spectral and spatial separation of two successive attosecond pulses. We might use this. Let's see a final confirmation for the really macroscopic quantity, the radially integrated attosecond pulses. What happens? It happens the following. if we don't do anything and keep the whole spectral domain, we have, please look at the, okay, please look at the black curves. We have emission 1 and 2. If we employ a low pass filter, we remain with emission 2, but you can see that with almost or with full we employ a high pass filter, we end up with only emission number 1 and without loss of energy of harmonic flux. Why this happened? It is obvious. This is just for a reminder.
Excuse me, Catalina, I think you should be concluding in 1 or 2 minutes.
Okay, 1 in 2 minutes. Exactly, I need 1 minute. Why this first emission does not contain the low energy part? Because it goes up to the cutoff is okay. But why it does not contain the low energy part? And trajectory calculation gives the answer for this. For example, if we look at the phase of the 201 harmonic order, we see that the phase of emission 1 continuously changes all along the propagation. It has no chance to phase match. While for emission 2, we have a good region of constant phase, which can be can find good phase matching conditions. And another aspect of this is that indeed in space, longitudinal and radial map of this harmonic order, we see it builds up in this region of the interaction region, and also the time-dependent phase matching calculation confirms that these harmonics have good high long coherence length exactly in that part of the medium where it good phase matching conditions. Then I skip the conclusions, so I stay within time. So I wanted to show how macroscopic high harmonic generation can elucidate some aspects of this complex phenomenon, which are not available nor experimentally, but anyway, single dipole calculations are not enough to capture these phenomena. Thank you. Okay.
Thank you very much, Catalina, for the nice talk. I don't see.
I see myself.
Any question in the Q&A? So we barely have any time for questions, but I'd like to ask just it's more curiosity. If do you foresee any interesting application of this lighthouse effect that you have described to study any specific problem in atoms or molecules that would facilitate this? I mean, the access to some information that with the the usual techniques is not so easy to access.
Not so easy to access. Yes, I would like to. Because I did not have time to say an application for the second one, for the spectral separation. We said a funny title for this work, I mean for this result, that 3 ways to select between 2 attosecond pulses, meaning that if we select or either the first one, either the second one, either both, and if we have both, for example, then we have a fixed time delay between them. So it would be a good fixed time delay, but different spectral content of these pulses. So this would be probably useful for attosecond pump probe experiments, where because this contains is very important that is exactly the laser pulse, yes, the driving laser period time spacing between these two pulses of different spectra contents. So this can be a palm probe.
Okay, that's very interesting. So thank you very much for your presentation. And so I think we must move on. And so I introduce the third speaker of the session is Michael Kinney from the University of Central Florida. And he's going to speak about new platforms for generating and characterizing fused cycle optical waveforms. So please, Michael, the stage is yours.
All right, thank you, Fernando. And I'd like to begin by thanking the organizers of this meeting for allowing me to present the latest results from my group. As Fernando said, my name is Mike Cheney. I'm from the University of Central Florida, and I'll be talking about new platforms for generating and characterizing fused cycle optical waveforms. Let's see. All right, so in the last several years, there have been a number of major advances that have been made in the area of high power ultrafast laser sources. And in particular, ytterbium-doped thin disk, slab, and fiber amplifiers have allowed the scaling of ultrafast laser powers from the 1 to 10 watt power level that's typical of titanium-doped sapphire lasers up to the kilowatt level and even beyond. And these lasers have been identified as a promising pathway to producing attosecond sources with unprecedented average power. However, attosecond science imposes significant constraints on the driving laser. This is because initiating attosecond dynamics and generating attosecond pulses both require laser pulses with durations close to a single optical cycle. So traditionally, these pulses have been generated by focusing a multi-cycle titanium-doped sapphire laser pulse from a titanium-doped sapphire amplifier into a noble gas-filled capillary. In this capillary, self-phase modulation occurs, which broadens the spectrum to cover typically over an optical octave now, and the pulses are then compressed using chirp mirrors. This is a technique that's now pretty standard in many laser labs, and it's fairly common to be able to obtain sub-2 cycle pulses, and in some really pioneering work, even sub-cycle pulses. However, it isn't quite so straightforward to adopt the same technique when using the longer laser pulses from ytterbium-doped lasers. This is due to the fact that the shorter input pulses from titanium-doped sapphire allow exposure of the gas medium to higher laser intensities. And the nonlinear refractive index, of course, is proportional to the intensity. And so exposing the gas medium to higher laser intensities means that you can achieve larger nonlinear phase shifts and therefore broader spectral bandwidths before the onset of undesirable effects such as ionization. The longer laser pulses from ytterbium-doped lasers have been compressed. So here's a few examples here. This is by no means a complete list, but this has required different levels of either engineering or scientific advances. So for example, using multi-stage compression, using extended nonlinear propagation in a very long hollow core fiber, in this case a 6-meter long hollow core fiber, or in work from my group using heavier atomic gases that have larger nonlinear refractive index. So in 2019, my group demonstrated the compression of a commercial ytterbium-doped laser amplifier by a factor of 20. So starting from a pulse duration of about 280 femtoseconds and compressing after the fiber to below 16 femtoseconds. This experiment was done with a stretched hollow core fiber, which we obtained from fused cycle, and it was filled with xenon gas. However, even though this is a pretty impressive compression ratio, it's still about 5 optical cycles, which is considerably longer than what is required for attosecond science. Now, unfortunately, we found that using gases with high nonlinear refractive index was just not sufficient for generating the bandwidth that was necessary for a single cycle pulse. So here I show the broadest spectra that we could obtain from xenon, krypton, and a diafluoroethane gas, all of which have large nonlinear refractive index, but with xenon being the highest. But all of them give similar maximum spectral bandwidths, and all of them support a pulse duration of about 15 femtoseconds. This had other advantages. So for example, this significantly reduced the cost of the gas that we used, since xenon is over a factor of 1,000 more expensive than the difluoroethane gas. However, we did find a bit of luck from an unexpected source, and we found a gas that did provide a broader spectral bandwidth than the others. This was nitrogen. This came as a big surprise to us, because typically, from my experience, I've always thought that nitrogen has a similar nonlinear refractive index to that of argon. And both the nonlinear refractive indices of nitrogen and argon are about an order of magnitude lower than that of xenon. So this was quite surprising. That so here you can see in black is the input spectrum. In argon is in the red spectrum here. Xenon is this orange one, and then nitrogen, which is the broadest, is here shown in blue. So this was a bit surprising, and we wanted to understand what was causing this behavior. So what we realized is that when you drive gas with longer laser pulses, the rotational dynamics of in this case a molecule can enhance the effective nonlinear response. This is because so while in atoms the nonlinear response is effectively instantaneous, it's the electronic response. In molecules, the nonlinear response is associated with both the instantaneous response from the electrons and also a delayed nonlinearity that's associated with rotation and vibration. For a linear molecule like N2, the rotational contribution can be quite large, especially if the molecules have time to align during the laser pulse. So for long enough laser pulses, this alignment can cause a very large increase or a large enhancement of the effective nonlinearity, and so therefore can enhance the amount of spectral broadening that we can obtain. So this is pretty straightforward to model. So in our case, we use a density matrix approach to calculate the time dependence of the ensemble average molecular alignment. And in this plot, I compare the transient nonlinearity of argon in the top and in nitrogen below, for both 30 femtosecond and 280 femtosecond pulses with the same peak intensity. What we can see in argon, unsurprisingly, is that the nonlinear phase shift is the same for both the short and long pulses. This is because the nonlinear phase shift in argon is just N2 times I, times I of t. However, in nitrogen, for the long pulses, the overlap of the pulse with the rotational response gives about a 5-fold enhancement of the nonlinear phase shift. We can also calculate the instantaneous frequency, which we see here in the right panel. And what we can see is that not only do we get a large enhancement in the frequency span, which you can see from the range, the vertical range of these plots, but we can also see that the zero crossing of this instantaneous frequency shift is delayed with respect to the peak of the pulse. What this means is that we more efficiently generate the red-shifted frequencies, and this causes an overall redshift in the broadened spectrum. We can test our model by comparing it to the supercontinuum spectra that we generate in argon and nitrogen. And we find that one-dimensional propagation simulations using our density matrix model have surprisingly good agreement with the experimental results. So importantly, the spectrum that we get from nitrogen is about 3 times broader than that of argon, and it already supports a 2-cycle pulse duration. And we can also see the strong enhancement of the red shifted frequencies in nitrogen in comparison to argon, which has a fairly symmetric spectrum. All right, so here is a comparison between the measured and the simulated spectra. Again, these simulations are not full propagation simulations. These are just one-dimensional model, one-dimensional propagation simulations based on our density matrix model. So now, armed with our model and with the knowledge that the enhanced nonlinearity depends on the rotational dynamics, we decided to try to find out what would be the best gas to use for spectral broadening with our laser. And we identified nitrous oxide as a great candidate, since our simulations showed that there was a strong enhancement of about a factor of 10 in the effective nonlinearity. And also, our simulations showed that this enhancement was strongest for a pulse duration of around 300 femtoseconds, which is the same as what we have from our commercial laser. So again, when we perform the experiments now with N2O in our hollow core fiber, we found that the measured spectral bandwidth agreed very well with the one that was predicted by our model. And at our highest pressures of around 4 bar, we were able to generate a red-shifted supercontinuum that covers 2 optical octaves of bandwidth from about 500 nanometers to beyond 2 microns. While this full bandwidth was larger than that we could compress with our chirp mirrors, we were able to compress a narrower bandwidth at lower gas pressure, which ranged from about 700 to 1400 nanometers using our chirp mirrors. And you can see here we were able to obtain a compression down to about 5.8 femtoseconds. This is below 2 cycles. And on the longer wavelength side, we borrowed a dazzler from Zhenghu Chang's group, and we were able to compress the long wavelength side of our spectrum between 1100 and 1800 nanometers to about 10 femtoseconds, which again is about 2 optical cycles. So this shows that the phase across the entire supercontinuum is well behaved and should support, in using the broadest spectra, it should support subcycle pulses. The compressed pulses we found are suitable for high harmonic generation. And so in this plot, I compare the harmonic spectrum that we generate with a xenon-filled fiber in the top. So this is containing more than 3 cycles. And for compression in N2O, which gives a pulse duration below 2 optical cycles in the bottom plot. And so what you can see is that in CEP integrated measurements, that the harmonic spectrum merges into a supercontinuum. Of course, in order to confirm that isolated out-of-cycle pulses are generated, we need to measure the CEP dependence of this spectrum, and that is something that we are actively working on. Interestingly, so our model does predict that the long wavelength components of the spectrum can be compressed using materials with normal dispersion. So you can see here in the left side of the plot that for the leading edge of the pulse, that the red-shifted frequencies are generated with a negative chirp, and so therefore can be compressed with normally dispersive materials. This behavior has already been shown experimentally by Francois Legaret's group. So in this case, they show for typical SPM, you get a positive chirp, all right? And so you need negative chirped mirrors in order to compress the pulses. But for this molecular gas, then you can get a negative chirp in the emitted supercontinuum, and then this can be compressed using fused silica. So in this case, they were using a Ti-sapphire laser, and that was stretched to several hundred femtoseconds in order to enhance this rotational response. And they were able to use bulk glass to compress the long wavelength components between about 800 nanometers and 1050 nanometers. This is much more of a challenge in the 1 to 2 micron spectral range where we're working, since it overlaps with the 0 dispersion wavelengths of most glasses. However, here I show some very preliminary results of a simple optical synthesizer, which is based on bulk compression in 2 channels, and using off-the-shelf optics that total about a few $100s. The results suggest that the redshifted supercontinuum that we generate in this molecular gas, in this case N2O, using ytterbium-doped lasers, can provide a very simple platform for generating few cycle pulses centered at around 1.5 microns. Unfortunately, there are some issues with the technique, and the main issue is that it's really not suitable for compression at high repetition rates. So here in this plot, we show the spectral bandwidth as a function of the average power of our laser at fixed pulse energy. And so what you can see is that the broadest spectral bandwidths can be obtained only at low repetition rates. And for the highest average power of 20 watts, the spectral bandwidth obtained in N2O is similar to that of xenon, and the energy throughput drops to below 30%. This behavior we now understand is linked to an increase in the rotational temperature of the molecule, which we can track by measuring the reduction in the spectral bandwidth on a pulse-to-pulse basis. And because this rotational heating is related to the internal energy of the molecule, it's very unlikely, we think, that this behavior can be mitigated by, for example, active cooling of the fiber. And really, we believe that this technique is most suitable for low repetition rate lasers of a kilohertz and below. All right, so next I'd like to shift gears a bit from generating to characterizing few cycle waveforms. So as we all know, accurate characterization of a laser pulse is critical to interpreting the results of ultrafast experiments. And for attoseconds experiments, of course, we have to go even a step further. It's not enough to know what the pulse looks like. We actually have to know what does the laser waveform look like, which consists of, the pulse, but also its absolute phase or carrier envelope phase. Now, we're all likely pretty familiar with the tools that have been developed over the years for pulse characterization. So many pulse characterization techniques have been demonstrated based on perturbative nonlinear optics, and these in general can be adapted to a single shot geometry. So for example, Frog, Spider, and D-Scan have all been demonstrated in single shot geometry now. On the other hand, these techniques are not sensitive to the absolute phase, and so therefore they can't measure the waveform of the pulse. On the other hand, it's been shown that strong field techniques and also techniques such as attosecond streaking or electro-optic sampling can measure the full optical waveform, but all of these have so far been generated in a multi-shot scanning measurement using a pump probe geometry. So we would like to combine both of these two advances in order to measure the waveform of a few cycle pulse in a single shot. Our technique is based on the TIPTO technique. TIPTO stands for tunnel ionization with a perturbation for the time domain observation of electric fields. And TIPTO was demonstrated by Kyung-Taek Kim's group in 2018. So in TIPTO, you have a strong fundamental pulse, which is used to tunnel ionize gas between two metal plates. All right, and you detect the current between those two plates generated by that strong pulse. Then you add a weak signal pulse or a weak perturbing pulse, which modulates the tunneling probability. And so by scanning the time delay between the fundamental and the perturbing pulses, the ionization yield maps out the electric field of the perturbing pulse. So that's shown here for two different values of CEP. Now, earlier this year, my group showed that the same technique could be adapted to a solid state material. So instead of measuring the ionization yield generated in a gas between two plates, we measure the band fluorescence generated in a zinc oxide crystal. So in this way, we showed that it was possible to map out the waveforms of mid-IR laser pulses with considerably lower intensity than is necessary to ionize gas. The use of the solid state medium has several major advantages over the gas medium. The most important of these is that we can take advantage of previously developed solid state devices in order to provide more functionality. So here in this work, we replaced the zinc oxide crystal with a silicon-based CMOS camera, and we introduce a small angular separation between the fundamental and the signal beams. By using the CMOS camera, we can excite the silicon medium nonlinearly, and we can measure the nonlinear excitation using the CMOS electronics. This also allows us to take advantage of the inherent spatial resolution of the camera in order to allow a single shot measurement. So by introducing this small angle between the fundamental and the perturbing pulse, and also by focusing the two beams with a cylindrical mirror, we're able to map the time delay axis to one of the spatial axes of the camera, which is very similar to a single shot frog geometry, but now using the camera as both the nonlinear medium and as the detector. All right, if we add a second harmonic pulse to the perturbation arm, this also allows us to access the absolute phase of the pulse, as I will show in a few slides. All right, so here's what the images look like on our camera. So on the top, you can see the excitation by the fundamental pulse only. And on the bottom here, you can see the combined excitation by the fundamental and the perturbing pulse. So as you can see, there are small modulations that are imprinted on the image, and these can be really clearly seen in the line out plot below. So then to extract the waveform, we use a very simple normalization procedure. This normalization procedure, we've shown it to be valid in both the tunneling and the multiphoton excitation regimes, and we can use this to obtain the waveform. The normalization is very robust, and actually we can retrieve identical waveforms for different time delays. So for example, if we change the time delay, then we shift this modulation pattern from this relatively flat region of the fundamental pulse to a region where the fundamental signal is varying. We can retrieve the same waveform regardless. All right, so next we need to generate CEP stable fuse cycle pulses to show that that we are sensitive to the absolute phase and the waveform of the pulse, and we do this using nonlinear compression in bulk silicon and YAG, as shown schematically here on the left. And this gives us a pulse with duration close to 2 optical cycles in the mid-infrared at a central wavelength of about 3.4 microns. We then characterize the CEP stability using a 2F to F interferometer. And so what you can see here is that the compressed pulses inherit the passive phase stability of the OPA source, and we can also control the CEP, as shown here on the left, by inserting, changing the insertion of a wedge pair in the beam. Okay, so in order to characterize the CEP of the perturbing pulse, it's necessary to set the absolute phase, or the CEP, of the fundamental pulse to 0. As I mentioned before, we can do this by adding a second harmonic pulse to the perturbing arm, and this is exactly what was done in the first demonstration of tiptoe. So here on how does this work? On the left-hand side, I show simulations of the second harmonic modulation strength for fundamental CEPs of 0 and pi over 2. And what you can see is that for the fundamental pulse with CEP equals 0, we get basically modulations with 2 components, 2 frequency components. The first is a strong component that has the periodicity of the second harmonic field, so that you see from these large peaks here. And the second is a weaker modulation at the fourth harmonic of the fundamental. So you can see this here in the Fourier transform. We have a strong peak at the second harmonic frequency of about 1600 nanometers, and we have a weaker peak at the fourth harmonic frequency. Now, when we shift the fundamental CEP to pi over 2, the second harmonic modulation decreases, while the fourth harmonic modulation stays the same, and so we're left with a dominant modulation at the fourth harmonic frequency. Okay, we can measure this in our setup as a function of the fundamental CEP, and what we find is that the amplitude of the second harmonic modulation yield is enhanced at for fundamental CEP equals 0, and it is minimized for fundamental CEP equals pi over 2, and our measurement is in pretty good agreement with our simulation. Okay, so now with the fundamental CEP set to 0, it becomes possible for us to track the CEP of the perturbing pulse. And so in this plot, I show measured waveforms for 2 different values of the perturbing pulse CEP. So these, you can see that the envelopes of the 2 pulses, or the 2 waveforms, are nearly identical. but you can also see the variation of the CEP from a sine-like waveform in red to a minus sine-like waveform in blue. Okay, so last, as I mentioned previously, the use of strong field excitation in solids allows us to take advantage of the properties of existing devices. And so in the case of the CMOS camera, we actually have a two-dimensional detector. This means that we can also track the variation of the waveform along a transverse spatial dimension of the beam. And so in this final slide, I show that we can imprint a dynamic wavefront rotation on the waveform. This is very similar to what was just shown in terms of the typical way of generating an attosecond lighthouse. And so we do this by inserting a calcium fluoride wedge prior to our cylindrical mirror. And so what you can see here is that we can measure this variation of the wavefront as the waveform as it's undergoing wavefront rotation. So here we show the waveform on the in the horizontal direction for different vertical positions within the focus. And you can clearly see this fanning out structure to the top or to the bottom, depending on how we insert the wedge. And so this is clear evidence for a wavefront rotation. And we can also take the Fourier transform of each vertical position, which gives us the spatial chirp of the beam. And we can compare that spatial chirp to one that we can calculate just through simple ray tracing, which is shown here in the dashed line with reasonably good agreement. All right, so in conclusion, we've demonstrated new platforms for generating fused cycle light pulses using rotational nonlinearity in molecular gases to enhance spectral broadening, and also for characterizing fused cycle light pulses using a single shot measurement that's based on CMOS technology. I'd like to thank the funding agencies who have supported this work, as well as my collaborators, Banggu Shim and Garima Nagar, who assisted us with realistic simulations of the rotational nonlinearity in fibers, which I didn't show in these plots, but it was really important to getting that, to understanding that, that phenomenon. I'd also like to recognize the people who did the work, specifically John Bitar, who's now at Berkeley, and Yang Liu. They led the experiments that I've talked about today. So this is kind of an old picture pre-pandemic. So a lot of the people in this picture have left for other places, and we have openings for students and postdocs. All right, and so last, I just want to let you know that we are hosting the 8th International Conference on Attosecond Science in Orlando in July 2022. You can check our website for the list of invited speakers, and we're expecting to open the abstract submission soon. So I hope to see you all in Orlando next year. All right. Thank you.
Thank you very much, Michael, for the nice presentation. I'm checking there is a question by Francesca Calegari. Thanks, Mike, for the nice talk and for waking up really early. I have a question on the first part of the talk. Francois demonstrated that MDSS is inducing spatial trapping. Could you please comment what you observe in the spatial beam profile?
So yes, so we definitely see something similar. In our case, it's a bit harder to measure the spatial beam profile, simply just because we don't have a nice infrared camera to measure it with. But we can clearly see in the visible part of the beam that the spatial profile is really a mess. And so the visible part of the beam being the short wavelengths, like well below the central wavelength, the spatial profile is kind of a mess. But after we filter out the short wavelengths, then we can see using a card or using multiphoton response of the camera, then we can very clearly see a very nice, well-defined beam profile.
Okay. I don't see other questions here. I have one. I like to understand. Okay, you mentioned that rotation is precisely the physical effect that is responsible for this spectral broadening of your pulse. And so I'd like to understand why N2O is better than N2. What is the key point? It's because is the rotation is slower, or what is the the key point here to understand why N2O leads to a broader spatial broadening.
Yeah, so there's two things. The first is basically the difference in polarizability along the two molecular axes, which is larger for N2O. And then the second is to try, it's about the time scale of the alignment. And so I think it's probably not correct to say that N2O is better for us because it aligns more slowly, but rather that we couldn't take advantage of the alignment of N2O if we used pulses any shorter. So but it is a kind of interplay of those two things, both the delta alpha difference in polarizability and also the time scale of rotation.
Thank you very much. Well, I don't see any further questions, so I think we are almost perfect in time. I think thank you very much, Michael, for the presentation, for waking up so early. What time is there? Is 5 a.m. maybe or something?
Well, it's 7 now, so it's not so bad.
Oh, it's 7 now. Okay, but you started at 5, basically. Okay, thank you very much. So I remind you that now you can meet the speakers in the breakout rooms that will pop up in your screen while I am speaking. So then you can discuss with them, ask any question you want, and so with this I conclude this session, and I hope to see you in the poster session after lunchtime. We have very interesting posters, and I recommend you to visit them. So thank you very much. Goodbye.